welcome to today's class. In today's class, we'll be talking about lone and bond pair electrons, region of high electron density, hybridization by Lewis structure. Now, what are lone pairs? Lone pair electrons, or lone pair for short, are valence electrons that are not involved in covalent bond formation. It is sometimes called non-bonding pair or antibody pair. It serves to distort the shape of a molecule or ions. Now, that means that lone pair electrons, they distort the shape of a molecule or ion. They are called non-bonding pair or anti-bonding pair. Now, bond pair electrons or bond pair for short, are valence electrons that are involved in covalent bond formation. They are electrons between two elements in a molecule or ion. They are presented by a short straight line. Bond pair electrons can be single, double, or triple bond. Bond pair electrons determine the actual shape of a molecule or ion. Now let's look at the Lewis structure of some molecules. Now let's look at ammonia, for example. N this is the Lewis structure of ammonia. Now if you look at the Lewis structure of ammonia, now 1, 2, 3 are bond pairs. So we have 3 bond pairs. And these 2 electrons that is on the central atom are called lone pair electrons. So ammonia has 3 bond pair and 1 lone pair electron. If you look at pair and 2 lone pair electron. Now let's look at thionite chloride, which is SOCl2. The central atom is sulfur. We have 1 lone pair on the sulfur atom. Now this is the Lewis structure of thionite chloride. Now if you look at it, you discover that the chlorine atom, the oxygen atom, also has a lone pair electron. But when we are talking about the lone pair electron in a molecule, we are only concerned with the lone pair electron on the central atom, not on the other atoms that is attached to the central atom. So in thionite chloride, we have 1 lone pair and 3 bond pair. So this is how to count and determine the bond pair in a molecule. Now, bond pairs can be single, bond pair can be what? Triple. Now, let's look at carbon 4 oxide. This is the structure of carbon 4 oxide. So you can see that carbon 4 oxide has bond pairs that are double. That's bond pairs that are double. Now, if you look at sulfur 4 oxide, the Lewis structure of sulfur 4 oxide is this. So you can see that in sulfur 4 oxide, we have 2 bond pairs. This is 1 and this is 2. Now the first bond pair is single, the second bond pair is double. So we have 2 bond pair and 1 lone pair electron in sulfur 4 oxide. Now let's look at region of high electron density. The region of high electron density, we abbreviate it in short, ROHED, refers to any area around the central atom where electrons are concentrated. It's equal to the sum of all bond pairs and all lone pair electrons surrounding the central element in a molecule or ion. Now let's look on the structure we've already drawn. Let's take ammonia for example. The region of high electron density of ammonia will be equals to how many lone pair? We have 1 lone pair plus how many bond pair? We have 3 bond pair, making what? 4. So the region of high electron density of ammonia is 4. Let's look at water. What is the region of high electron density of water? We have 2 lone pair plus 2 bond pair. Again, we have 4. In thionite chloride, the region of high electron density will be 1 plus 3, giving me a total of 4. Let's look at carbon 4 oxide. The region of high electron density will be, there's no lone pair. Now we have what? Bond pair. Now, when you are counting region of high electron density, this bond pair that is double will be counted as 1, plus this bond pair that is also double will be counted as what? 1. So the region of high electron density of carbon 4 oxide is 2. Now let's the region of high electron density of sulfur 4 oxide. It has 1 lone pair plus 2 bond pair. Now this, the first bond pair is single, the second bond pair is what? Double. We are still going to count there 1 plus 1, making 2 bond pair. The region of high electron density is 3. So the sum of all lone pair and bond pair surrounding the central atom in a Lewis structure is what we call the region of high electron density. And that refers to what? The concentration of electron around the central atom. Now, the region of high electron density is very important. It is used to determine the hybridization. It is used to determine the hybridization of a molecule or a ion. Now, what is hybridization? It's simply what? The mixing or blending of 2 or more atomic orbitals of the same quantum or energy level to form a new set of orbitals known as what? Hybrid orbital. Now, if you look at the subshells, we have the S subshell, the P subshell, the D subshell, and the what? The F subshell. Now, the S subshell takes a maximum of 2 electrons and it has 1 orbital. The P subshell takes a maximum of 6 electrons and it has 3 orbitals. The D subshell has maximum of 10 electrons and it has 5 orbitals. Then the F has 14 electrons and 7 orbitals. Now, these things, we combine it to form what? Our hybridization. Now, let's look, for example, again. Let's go back again to the Lewis structure of BF3. Let's look at BF3. Now, this is the Lewis structure of BF3. Now, we have considered how to draw a correct Lewis structure. If you missed that lecture, go back and do justice to that. Now, if you look at BF3, the region of high electron density is what? Is 3. Now, if you go to atomic orbital, let's look at the atomic orbital again. We need 3 what? Atomic orbital, because the region of high electron density is what? Is 3. So the subshell S can give me 1 orbital. The P shell can only give me 3 orbital. D 5 orbital. F what? 7 orbital. Now I need what? 3 orbital, because the region of high electron density is 3. So I will get 1 in X. X will give me 1. 1 from 3 remain 2. P can give me a maximum of 3, but I need 2. So I will get 2 from P. So we have the region of high electron density to be 3. So 1 will be S, and then the remaining 2 will be what? P. So this is sp2 hybridized. Now let's look at ammonia. Let's look at ammonia. You must learn the Lewis structure because it helps you to determine hybridization in an easy way. Now the region of high electron density is what? Is 4. So I need 4 atomic orbitals. S can only give 1, then P can give me 3. Give me what? Hybridization of what? sp3 hybridized. Now, if I consider sulfur 4 oxide, the region of high electron density is what? Is 3. Now, because it's 3, the hybridization will be what? sp2 hybridized. Now, let's look at carbon 4 oxide. Now, if you look at carbon 4 oxide, you will discover that the region of high electron density, is 2. If it is 2, we have X will give us 1, then P will give me 1, making what? Carbon 4 oxide to be what? sp hybridized. Now, let's look at I3 minus. I3 minus, we have 1 iodine at the center and the remaining 2 distributed around it. We have 3 lone pair. If you have checked our Lewis structure, structures class. Now, if you look at what is the region of high electron density here. Now, the region of high electron density, we have 3 lone pair plus 2 bond pair. Give me what? 5. Now, how do I count my hybridization for 5 orbital? Now, X can only give me 1. So, S can give me 1. Remaining 4. P can give me 3. That is 4 orbital, remaining 1. Then that means we are in D. D can give me 5 orbital, of which I just need only 1. So the hybridization of I3 minus is what? sp3d. Now let's look at PCl5. PCl5 we just have the structure like this. There's a chlorine atom here, another chlorine atom. We have drawn this structure before. Now, the region of high electron density of PCl5, so 1, 2, 3, 4, 5. Again, that gives me what? 5, which will give me hybridization for sp3d. Now let's look at BRF5. Now this BRF5 has 42 electrons. So we have bromine as the central atom. So we complete the octet structure of the fluorine. So we have 5 fluorine making 40 electrons. Then we have 2 electrons on the what? On the bromine atom. So our region of high electron density, we have 1 lone pair plus 5 bond pair making 6. So what is the hybridization? Now X orbital can give me 1, S subject can give me 1 orbital, P subject can only give me 3 orbitals. So we have used 4 orbitals out of the 6, remaining 2, in which D can give me 2 orbitals. So the hybridization is sp3d2. 3 minus is a resonance molecule. So this is the Lewis structure of NO3 minus. The region of high electron density will be just 3 bond pairs. So we have 3, and our hybridization will be 1 in S and 2 in P. Let us look at ozonium ion O3+. The Lewis structure is so the region of high electron density is 1 plus 3 making 4. So the hybridization will be what? xp3. You can also do for ammonia. You can find the hybridization of ammonium ion, and you will get sp3. Now, this is the easiest way to find the hybridization of a molecule. You look at